So today we're looking to have Freddy Bouchet from ENS Lyon. So Freddy did his PhD in Grenoble in the early 2000s and had various postdoctoral positions in Italy and in France, and has been in Lyon at CNRS and ENS Lyon since 2010. And he'll be talking today about abrupt transitions for turbulent atmosphere and climate dynamics.
So thanks a lot for inviting me at this seminars. So my specialty is statistical mechanics applied to fluid mechanics, specifically turbulent problems and the climate. New tools in order to study phenomena which are hard to study using a conventional approach. So one of the things we have studied a lot during the last 5 to 10 years are rare events. And so there are different kinds of rare events which are very important in turbulent flow. And so this is what, so there are two kinds of rare events, events that have a huge impact and events that produce transition from one attractor to another. So today I will discuss this second kind of example, and I want to discuss two applications, one for Jupiter troposphere and another one for abrupt transition to superrotating atmospheres for Earth-like atmosphere dynamics. So yes, please ask me any question whenever you like. So I will begin by introducing rare events, introducing the phenomena I am interested in, and then I will talk to you about instanton theory. Instanton theory is a theory in statistical mechanics that explains why the dynamics that leads to rare events are often predictable and why the path that leads to these rare events can be predicted. And this path is called an instanton. So I will explain you. This is a piece of classical theory in statistical physics. And then I will show you how we have applied this for Jupiter dynamics. And then we want to go towards more towards phenomena which are more related to Earth dynamics, and we began recently to work on abrupt transition to superrotating atmosphere for the Earth. So this is just an example of what we would like to be able to do on the long term. I mean, this is the temperature in the North Atlantic area for the Earth during the last glacial period. So this was 10,000 years ago, and this was 60,000 years ago. So this, and the current climate is here, you cannot see it. And so the current climate is a warm climate. And so this is the last glacial period, basically. And so you can see two curves. A blue one, which is comes from ice core, and a green one that comes from sediments data in the North Atlantic. Both comes from the North Atlantic area, and so they are both proxy of temperature. And so you can see the temperature on the here. So you see fluctuation of temperature of the order of a few degrees, 4 or 5 degrees. And what is very interesting is that there are abrupt changes of abrupt transition between different states or regime of the very complex dynamics of the ocean coupled to ice and coupled to the turbulent atmosphere. And so those transitions here, they are not driven by external parameters. The transition from glacial to interglacial period are driven by external parameters. But the one inside the last glacial period are not driven by external parameters. They are just due to the very complex dynamics and the natural variability of these very complex dynamics. And so the key point is that for studying these events, it is very difficult because you would like to have a comprehensive model with a good dynamics, which is already quite challenging. And then you would need to run it over thousands of years, tens of thousands of years, which is even more difficult if you really want to have comprehensive model with the good dynamics. And so this is one of the challenge we would like to address on the long term, how to be able to compute these relevance and to study them scientifically. So let me show you another example. So this is a Jupiter troposphere. So you can see here the bands on Jupiter troposphere, and the color of the bands are directly correlated with the vorticity of the flow in the upper troposphere of Jupiter. So the fact that there are bands show you that the flow is basically the velocity field is mainly from east to west. And so you can see here the velocity profile on the right, the velocity on the x-axis, and the latitude on the y-axis. And so you can see that you have about 10 alternating eastward and westward jet for each hemisphere. So the velocity are huge, about hundreds of meters per second. And so there are two curves on the right plot. One comes from Voyager data and the other from Cassini data. And so you see that in between these two spacecraft, 25 years has passed, and during this period, nothing has changed much. You see that the velocity profile are nearly the same. So the turbulent atmosphere here reach stationary states, and it reach effectively on the larger scales, it remains stationary for extremely long time, decades, maybe centuries. So the key idea I want to stress today is that it has not always been like that. I mean, during the period 1939-1940, one of these jets suddenly disappeared and produced anticyclones. So the anticyclones that have been produced are the three white ovals you can see here on these plots. And Phil Marcus called this Jupiter's abrupt climate change. So it's basically a change in the organization of the in Abrupt. It lasted a few weeks, a few months maybe, and then nothing particular happened during many decades. So this is one other examples of such a strong and abrupt transition. So I will try to connect this to basic theories in statistical mechanics. So let me introduce you to this theory. So the point here is to study transition from attractors, from one attractor to other attractors. So I will use a very simple framework where I have a dynamical system. dx over dt is b of x. Here x is a vector in dimension whatever. B is a vector field. And so I will assume that the dynamics dx over dt is b of x as a 2 or 3 or more attractors. And so basically what's happening for this dynamics is that x goes to one of these attractors and then stay there forever. Except if you begin to add some noise, as I have done here. So I have added a small Gaussian noise. So this noise, this function here as a Gaussian statistics, which is delta correlated. And there is a number in front of it, which quantify the amplitude of this noise. So I will assume here that epsilon, the amplitude of the noise will be small. So because so in the statistical physics, one is used to represent the transition probability using path integrals. So on the left-hand side here, I have the probability to go from a state x0 at time 0 to a state xt at time t. So this represents the probability of a transition from one state to another. So you can compute this using, for instance, the Fokker-Planck equation, but you can also compute it through a path integral. So a path integral means that you have to integrate over all possible paths. This is the meaning of this symbol. And then you have to associate to each path a weight. So the weight here is the exponential of minus an action divided by epsilon. So to get this this number, I mean the weight of a path, you just take the weight of a Gaussian fluctuation here from the noise, and then you make a change of variables from eta to x, and then you get this factor here. And so when you make this change of variables, you get that a of t is the integral of 0 to t of L of a Lagrangian of x and x dot. And the Lagrangian is nothing else than x dot minus b of x to the square. It is to the square because the noise was Gaussian. And there you have a one-time integral because the noise was delta correlated in time. So this explains the weight you have to put here for each of these paths. And then in order to estimate this, we will use an asymptotic expansion when epsilon is small. Then you see that we make an integral with the exponential of minus something which is very large. And so this is called the Laplace integral. And so probably you know that a Laplace integral like that, it will be completely dominated by the contribution of the minimum of the action. It's easy to understand because all values that are not close to the minimum of the action will be exponentially small compared to the one of the minimum of the action. And so that's why we will have to compute the minimum, the path which minimize this action, and then we can add some constraints. For instance, if we want to compute this transition probability, we need to constraints on the fact that x of 0 is x naught and x of t is xt. And so then at the leading order, this transition probability will be given by the exponential of minus this minimum of the action divided by epsilon. And so it's an estimation of this probability, but it's a bit more than that because the whole framework tells you that the paths that actually contribute are concentrated close to this minimum of the action, and they are concentrated in a range of the size of a square root of epsilon if you try to expand around this minimum. And so this is what is illustrated on the next slide. Here I have I illustrate just an example where b of x is minus dv over dx, and x has two components, x1 and x2. And so what you can see on the plot are the level lines of this potential v. And so you can see that there are two minimum, one minimum here and one minimum around there. And so you have saddle points in between these two minimum. And so this red path here is exactly the minimum of the action with this condition. And so this minimum of the action is what I will call in the following of the talk an instanton. And so then the white path is one realization making a numerical simulation of this dynamics of a path that actually goes from one attractor to another. And so then you can see that this white path has very precisely follow the red path with fluctuation, and the fluctuation are of order of a square root of epsilon. So basically with this theory, we have explained that the transition from one attractor to another should closely follow the instanton, the red path, and then you can compute the transition rate given by this formula. So in the case where there is a potential, the transition rate is actually the exponential of minus delta V, the difference of the value of the potential at the saddle points and at the attractor, divided by the noise. And in statistical mechanics, often the noise is just the kBt, where T is the temperature, and we call this an Arrhenius law. So the question is, is this relevant for turbulent flows? And so this is what I will illustrate you afterwards. And here I will describe better this figure afterwards, but here you can see a picture that we have computed that illustrates that jet like Jupiter jets actually follow this instanton phenomenology. So I will explain you this better later on. So we have tried to study the instanton behavior in many kinds of complex dynamical systems. So we did that recently, for instance, in order to study collisional trajectory in the solar systems, where the dynamics is the dynamics of the 8 main planets of the solar systems, which is chaotic. And on time scale of billions of years, you can have collision. And then with Eric Wallace, a PhD student, we have shown that the collision in the solar systems, at least in simplifying models, are actually driven by an instanton. So this has recently been published and featured in Nature Review Physics. So let me go back to the to tell you a bit more about instanton for Jupiter's abrupt climate change, and then I will try to go towards the application for the Earth atmosphere. So for Jupiter, we have been studied a simple model, which is the simplest possible turbulent model of Jupiter troposphere. So in the community of geophysical fluid mechanics, this is considered as a toy model for Jupiter. So this model is not quite realistic from a quantitative point of view, but still it is turbulent, and it has all the main mechanism of Jupiter troposphere, and it actually the prediction of the bands and the width of the bands and their main properties are quite good at a qualitative level. And so this model is called the barotropic quasi-geostrophic equation. So it's the model for a flow in one layer. So it describes velocity field V, which is a two-dimensional velocity field. So then once you have a velocity field, you can compute the vorticity. Omega is the curl of the velocity, which is a number when you have the flow on a plane. And then you can compute Q, the potential vorticity, which is omega plus beta y. Here y is the north-south coordinate, and beta is a number which is related to the way the Coriolis force change with latitude. And so this is basically related to the way the Coriolis force change with latitude, linearized close to reference latitude. And so this Q, when you make asymptotics of the Navier-Stokes and the primitive equation with some hypotheses, you can show that it follows this equation. So where Q is just transported by the velocity, there are some kinds of dissipation. For instance, here we have used viscous dissipation and the linear dissipation. And we also add a random force that is related to the unresolved scale. And here it's mainly related to the three-dimensional convective plumes. So I will not go much into the detail for the study of this model. I will just show you a few qualitative aspects. So here what you see is this vorticity field. So you have blue points which corresponds to cyclones, red ones that correspond to anticyclones. And so you have thousands of small vortices, and it's in a doubly periodic domain. And so you see that these vortices, they coalesce to form bands. And so here you can see that they form two bands, two blue bands and two red bands. So what you can see on the top plot here on the right is the average vorticity field in red. So it is average in the x direction. So then it's the vorticity field as a function of y. And in green, you can see the velocity field as a function of y. So you see here actually that you have two jets, two eastward jets, the tip here, which have this very characteristic cusp-like shape, and then two westward jets, which are much smoother. And those are actually properties of Jupiter jets. So on the left, on the top left plot, you see a Hofmüller plot where you have time on the x-axis, and on the y-axis you have y actually, and the colors are this time average. Sorry, not time average, x average vorticity. So you see clearly the two bands, and you see clearly that they are stable and stationary over an extremely long time scale. And so the point is that for many reasons I don't explain today, we were guessing that there were a possible transition in this for some parameters. And here we have chosen a value of a parameter for which you have over extremely long time transition between two jets and three jet states. So here you see time again on the x-axis. On the y-axis you see again y, and the color are the zonally average vorticity. And you see two jets initially, three jets, two jets, and so on and so forth. And so on the bottom plot, you can see the Fourier decomposition of the field in this direction with wave number 2, the red plot, and with wave number 3, the black plot. So basically when you have two jets, Q2 is large, and when you have three jets, Q3 is large. And so you can see that these two numbers here, the modulus of the Fourier component, they nicely monitor the jet properties. So you see that there are here 5 transitions. So here alpha is very small, something like 10 to the -3. So we got 5 transitions during something like 4 10 to the 6 turnover times of the systems. So those transitions are extremely rare, just like on Jupiter. And so this is the point. I mean, so they were not observed before because they are so rare. And the question we ask is how to predict those transitions, how to study them, how to compute their probability, and do they follow actually the simple theory that I was explaining in the introduction? Can we expect instanton to occur for this dynamics, and how to study this? So in order, it's a very long story. I will explain you just a very short part of the story. One key point is that we have used the algorithm which is called Relevance algorithm, which allow to oversample and simulate a lot of these rare events. So for instance, in this case, we use an algorithm which is called the adaptive multilevel splitting, that was developed by Serroux and Guyader and studied mathematically in the group of Tony Lelièvre. But the idea is always the same, and the basic idea comes from Kahn and Harris in 1953. So here let's assume that we have 2 attractors. So A here is an area of the phase space where you have the first attractor, and B is the area of the phase space where you have a second attractor. Then what I will do ensemble simulation. For instance, starting from here, from X, I will make n trajectory. So n is 3 for this sketch here. So I will look at how far this trajectory go towards B. So in order to measure this, I defined a function Q, a score function Q. And so you see the dashed lines here are the level lines of this score function. So here you see that the trajectory 1 was the worst one. So I will throw it away, and I will replace this trajectory by another one that I will start from the initial condition taken from the trajectory 2 on the same level line for the function Q. And then from here, I will simulate a new trajectory. So this new trajectory, the purple one, will be better than the trajectory 1, and it will go in the direction of B. And then I will do this recursively, and very efficiently, I will be able to produce thousands of trajectories that actually go from the attractor A to the attractor B. So it's much more efficient than just waiting for this to happen where most of the time nothing happens actually. So doing this, you can actually estimate also the probability. So at each step of the algorithm, you keep n trajectory, you keep n-1 trajectory among n. And so then the probability at each iteration is lower than the previous iteration by a factor 1 minus 1 over n. So the estimate probability of the path then is 1 minus 1 over n to the kappa, where kappa is the iteration number. So then there are nice mathematics that explain that this is correct and tells you about condition for this to work actually. So we have used this for this turbulent flow, and so we were able to get thousands of transitions, while here with the dynamical approach, the direct approach, we were able to get just 5 of them. And moreover, we were able to change the parameters and to study the Arrhenius law for these problems. And so doing this, we were able to make this plot where here you see again Q2 as before. Here it's Q2 square, Q3 as before, Q3 square, and Q4, which is the wave number 4 Fourier component. And inside the red blob, you have 90% of this 1000 transition that goes from attractor A to attractor B. So here you have the 2-jet attractor, here you have the 3-jet attractor, and you see that most of the transition, they follow basically the same path in this reduced description. And so this is exactly the instanton behavior I was describing before. And so our conclusion is that so the blue blob is the same for the backward transition. So here the conclusion is that we actually have for this turbulent flow the same phenomenology as was described for these very simple dynamical systems. But actually, when you write the turbulent equation, it has not this very simple form where you have a simple vector field which has point attractors with a small noise. And so there is much more in order to understand this behavior. So we have done a lot of theory for that, but I will not explain you this today. I just wanted to give you the hint of the kind of work we are doing with this. So the conclusion for this part, for the Jupiter's abrupt climate change, is that we have computed a rare transition, very rare transition between these zonal jets. They are similar to Jupiter's abrupt climate change. They cannot be computed using direct numerical simulation because they are too rare. So the transition actually follow an instanton phenomenology, and something I have not shown you today, they also follow an Arrhenius law. And then we have a set of theoretical work in which we actually try to go towards more theoretical approach to study this relevance and this transition. And one of this approach is actually very close to the the cumulant expansion at order 2, which has been developed a lot by Steve and others. And so, for instance, we have worked a bit on this with people working in this community, for instance, with Brad working at Brown University. Do you have a question for this part?
Can I ask one, Freddie? Can I ask your scoring, your big Qs?
Yes.
So does it? How do you choose? I mean, in your drawing, it's kind of obvious how to choose a distance and a kind of scoring system. Yeah. Is it obvious in a very high dimensional system?
No, not at all. It's not obvious at all. So I mean, so here we were lucky because it turns out that the phenomenology of the transition is quite simple. So we were able to guess a good Q. So if your Q is not good, then you may select trajectory that goes in the wrong direction.
Yeah.
So it might be worse than anything else. And so this is really an important point and an important question. So either you think you understand already qualitatively your systems and you choose a nice Q and it will work, it will be wonderful. Otherwise, I mean, you can try, it can work or it can fail. So in many cases, we have studied, we were failing quite badly. So what currently we are trying to use machine learning in order to learn Q from a few trajectories, a few transitions, such that even when we don't understand qualitatively what should happen, we might be able to use the algorithm.
Yeah,
but, you're right. The choice of Q is a critical thing.
Yeah, that's interesting. Thanks, Freddy. Thanks.
Okay, so this was the second part of the talk. Now we would like to do exactly the same kind of things for abrupt transition that are actually relevant for Earth climate. And so there are many examples in the Earth climate of such transition in the past, as I will show you afterwards. So I will change my slides. And so one question is which one to choose. So we have chosen to study something related to atmosphere dynamics. So possible transition to superrotation. And the main reason why we have done that is that we think that for those, the dynamics is actually quite well represented by the current models. So this work, I mean, has been done in a collaboration with Corentin Herbert. Corentin is a young, very smart researcher here at INS de Lyon and the CNRS. And with Rodrigo Caballero. Rodrigo is a colleague from Sweden, from Stockholm. And so we want to study abrupt transition to superrotation atmosphere. So here we have to go back one step, because here it's not even clear whether such a transition, well, such transition exists, but it's not clear whether they should be abrupt or not. I mean, from the point of view of dynamical systems or statistical mechanics, the question is whether the transition will be discontinuous or whether they will be continuous. And so this will be the main question I will address here with this. So here, before that, I want to show you these slides where you see many examples in nature and in experiments and in numerics of abrupt transition in turbulent flow. And so this is, for instance, in rotating tank experiments, in three-dimensional turbulence. This is in a rotating tank experiment in geostrophic turbulence. This is MHD experiments where you have change of polarity of a magnetic field, which are akin to the change of polarity of the Earth magnetic field. And this is basically the same as what I was discussing before. And so there are thousands of examples. So it's natural to expect that many complex dynamics should have such transition, even if often people don't expect it, just because it takes extremely long to see them, actually. So that's why they have been seen mainly in experiments rather than in a numerical simulation. So this is an example of glacial interglacial abrupt transition, which, as I was saying before, are driven. They are driven by the change of the astronomical parameters of the planet. But those are the yellow bands here. But inside the black curve, if you look at the black curve, in between the yellow band, you see that you have a dynamics which is quite fluctuating a lot during the glacial period. And so this is exactly what I talked to you about with my first slide. And here you see another data set where you see, for instance, if you look at the bottom part, you see that the transitions are extremely abrupt. The transition here from the data in the I-score, we see that the transition lasts maybe something between 1 and 10 years. So they are very abrupt at the geophysical scale. But we won't be able to study this because the dynamics is too complex. We will go towards another kinds of possible transition, which is called superrotation. So I want to begin by explaining you what is a superrotation. So here you can see a picture that comes from a classical paper by Isaac Held, where you see the velocity of planetary atmospheres simulated in a model. And so you will see many of these plots where on the x-axis you see the latitude, and on the y-axis you see the speed of the wind, where the wind has been zonally average, meaning average in the xy direction, and also average in the z direction. And so here you can see that in this model there are two states, one state with a black line and one state with a dashed line. So the state with a black line is called the normal state with this n here. And so you see that the wind has two maximum at mid-latitude, here and there, one in each hemisphere. And this is called the jet stream. And so this is very akin to the actual states of the Earth, where you have two jet streams at mid-latitude. If you look at the equatorial part, close to latitude 0, you see that there is a very weak westward jet, but it is actually very weak. And so for the other state, which is called the superrotating state, you can see that it is quite different. You still have two maxima here and there with mid-latitude jets, which are more like a subpolar jet, closer to the equator. But the main difference is that now, close to the equator, you have a velocity which is which is positive. So at the equator, you see that the velocity is faster than the velocity of the planet. And so that's why it is called superrotating, because the velocity of the atmosphere moves faster than the velocity of the planet. So this is a bit, this is striking, because if you look at angular momentum conservation, the maximum of the angular momentum is at the equator. And so if you write the angular momentum here this way, where A is the radius of the planet, phi is the latitude, omega is the rotation speed of the planet, and u is the actual fluid velocity in the xy direction. And so this is the angular momentum with respect to the axis of rotation of the planet. And then you see that you should not expect, I will make the following reasoning. I start with a fluid particle from this point, from latitude 0, and I consider where the angular momentum of the planet is maximum, and I consider conservation of angular momentum. And if I do that, I find a u which is given by this um, here, just by conservation of angular momentum from the equator. And this um is plotted here. And so you see that the normal states of the atmosphere actually has a velocity field for which the value of the angular momentum is very close to the conserved value for the angular momentum from the latitude 0, from the equator. But you see that the superrotating state has actually an angular momentum which is larger than what you should expect just by conservation of angular momentum. And so there is something to be explained for these states. So the theory for these states is kinds of classical, but I will remind it to you. So the first thing is that most of the planets in the solar systems have a superrotating atmosphere. This is not the case for the Earth currently, but Venus has, Saturn has, Titan has, Jupiter has, and actually many extrasolar planets have a superrotating atmosphere. And this is what we observe. So basically, it seems that superrotation is the rule rather than the exception. And actually, in the numerical simulation, I show you here two examples, one with a shallow water equation and one with a primitive equation. This is very classical to obtain the superrotation. So from the point of view of fluid mechanics, if you look at the zonally average equation for the velocity u, so this is the meaning of this u bar e, you write the equation. So you get terms here in pink that are all the transport term, the inviscid transport term, and basically these pink terms, they conserve angular momentum. You have dissipation terms that will mix it will mix angular momentum. And then you have a boundary term that restore the value of the angular momentum to the value of the planet. So if you would have only this pink and the green terms and the boundary terms, it would not be possible to have superrotation. In order to have superrotation, you have to count on the blue terms, and the blue terms is what is called the Reynolds stress or the eddy momentum flux convergence, which is due to the average effect of the fluctuation around the mean state. And so this is, you have to count on the effects of this fluctuation in order to produce a flux of angular momentum and a source of angular momentum at the equator. So then the question is, which physical parameters control superrotation in a planetary atmosphere? So I will give you a classical answer to this. But then I want to go further than the classical theory, because what I want to ask is whether the transition might be abrupt. And so for this, I will explain you when we change those control parameters, could transition to superrotation in Earth-like planet or for other planets be abrupt? This will be my main question. And if they are abrupt, could we have a very rare transition from one attractor to another? What I will call bistability between normal and superrotating state for the atmosphere. So today I will present you the first point, which is a classical point, and a second point, which is a work we have done. And for now, we have not yet begun to study the third point, but this is what we plan to do in the future. So the classical idea is that superrotation can be forced by waves, turbulent waves. So for instance, Rossby Kelvin waves in the case of the planets. So this is a very old idea. In general, in geophysical fluid dynamics, you can produce jets by the effect of the waves or the effect of the turbulent fluctuation. And so this is a picture that comes from a lecture of Bill Young, where this is illustrated in the simple beta plane model, which is the same model as the quasi-geostrophic model I was discussing in the first part of the talk. And so here it has artificially, just for the purpose of the illustration and for the purpose of basic study, what has been done is to force the flow just in a small narrow band here. And so the flow is forced in this narrow band. It produces this turbulence, and this turbulence will induce Rossby waves, so which are represented here by these blue lines. And so the Rossby wave has a group propagation from where the flow has been forced away, so group propagation in this direction and that direction. You have phase propagation, which is like that. And then when these waves are dissipated, they will actually, I mean, this wave will actually transfer angular momentum from where they have been produced to where they are dissipated. And if you look at the mean effect, here you see this small plot. it produces a jet. Here it produces where the waves have been forced, it produces eastward jet, and where it is dissipated, it produces a small westward jet. And so this is the classical mechanism for producing these zonal jets. And this classical mechanism should actually apply to the equator. So close to the equator, I mean, what people have done classically is to study, for instance, the very simple shallow water model, linearized close to the state of rest here for this first part. So you see an equation for u, v, which are two components of the flow, and h, which is the height of the field. And this simple dynamics has been forced by a forcing term q, and it has been here it is linearly dissipated, and this is called the Matsuno-Gill problem. So here I will use a forcing term that has the shape represented on this plot. So here this is just x and y, and those are the level lines of this q here. And so you see that I have chosen a q which has a wave number 1 in this case. So there are many reasons to do that. For instance, one reason could be that the top of the atmosphere insolation has a wave number 1. So this might be relevant for extrasolar planet, or but there are other reasons for the Earth to do that. So if you do this simple exercise, then to study the response of this dynamics, then you will see this kinds of picture here. So this is the H field, which is represented in color. And so the white line are just the isoline of Q, and the colors are the isolines of the response for the H field. And so you see it produces this dumbbell shape response, which are produced actually by exactly the mechanism I was describing before. The forcing forces Kelvin and Rossby waves. They go away from the equator, and then they produce these kinds of H field. And just to show you that this is relevant for the Earth, you can see on the right plot the annual mean geopotential height in contours, which is plotted from reanalysis data, which are very close to actual data for the Earth. And you see that there is a shape here, which is basically the same as the shape of the Matsuno-Gill response. And so basically here the forcing comes from the monsoons and the convection in the Indian and Australian area, which is the main forcing. And so it's a bit more complex. You have other forcing that produce other things, but you see that this is qualitatively relevant. Then we will change a bit the problem by adding a constant flow U here. And then you have the same Rossby waves and Kelvin waves, but they interact with the constant flow U. And what we want to do is to study the response of these Matsuno-Gill problems as a function of U. And so you see on this plot, U, we will change U. And you see on here Y, and the colors represent the momentum flux convergence. So you see that, for instance, for U equals 0, you have a very strong forcing of a jet here towards the equator, eastward jet, and forcing of westward jets at the flank of the tropical area. So it's exactly what was described here, or what you were seeing here before. But now you see how this change when we change U. And so you see that when we increase U, actually the response increases. So this is a positive feedback. It increases until it reaches a maximum, and then it decreases. And so the reason why there is a maximum here is because there will be a resonance between the velocity U and the phase speeds of the Rossby waves. And so what you can see on this plot is actually a resonance picture for the interaction between the Rossby waves and the mean flow. And so using this ID, so several people, for instance, here it's Arnold, Zipperman, and Farrell, they have put these kinds of forcing in an actual three-dimensional model of the Earth atmosphere, and they were showing the same kinds of response and the fact that it actually produces a superrotating atmosphere. So here the first conclusion is that one key parameter to control superrotation is the strength of the non-zonal forcing, which force Rossby Kelvin waves. Now I want to address the main question: can this abrupt transition to superrotation, can this transition to superrotation be abrupt? So I want to change the physical parameters and to see the response. So what I will call an abrupt transition is a transition like on the right part of the plot, where when you change the control parameter, here the forcing, you will get two branches and a range of parameters with a bistable situation. If you want to have this, you should have a bifurcation. And if you have this, if you look at what's happening from the point of view of a response of the systems, you realize that you need, along these unstable lines, a response which go this way in order for these lines to be unstable. So it means that the force you get here should increase when you increase, at least in this area. So it means that you need somewhere to have dF over du larger than 0. So you need some kinds of positive feedback. So where does such a positive feedback could come from? And so classically, there are two answers. One is from the Hadley cell. It is a feedback I will not describe today. And the other possibility is that there would be a positive feedback through the momentum flux convergence. And so this positive feedback through this momentum flux convergence, it's actually exactly what I described before. If you look at here this plot, you see that the forcing of the mean flow is actually increasing here when you increase the mean flow itself. And so this is indeed a positive feedback. And so with Corentin and Rodrigo, we were able to make a bit of analytics for this, to compute the forcing and to make this plot, and also to show that it is actually a resonance behavior with the resonance which are given here. And so you see here the main thing would be the value of u compared with the value of minus the CR, where CR will be the phase speed of the Rossby waves. So this is then this momentum flux convergence with this resonance, which is plotted here, should be balanced by the friction. And this is what we show here. We have the balance between the blue curves, momentum flux convergence, and the friction. And you can see on this plot that there are three equilibrium for this balance. You have two stable ones and one unstable here. And whether this will be the case, whether you have just one attractor or three, will actually depend on how peaked is this resonance. And so basically we were able to explain which are the good control parameters to have not just the resonance, but actually to have a resonance which is strong and peaked enough such that when you balance it with the friction, it gives you abrupt transition. And so the good control parameters are the ones that are described here: K, the wave number forcing; CR, the Rossby wave phase speed; and epsilon, something related to friction. And then what matters will be the width of the bistability range, which will actually be of the same order of magnitude as the value of the phase speed for the Rossby wave. Sorry, I am a bit fast because I realize that I am late. But what we did afterwards is to check that such bistability actually occur here in an axisymmetric model of the Earth dynamics. And you can see here, which, for instance, let me describe the blue curves. We change the forcing amplitude Q. So when we increase Q, we go along the blue curve, we are on the first attractor. And so you see that the zonal wind is rather weak. And then suddenly jump to another branch, and where we are in the superrotating state. And then we can still increase Q, we stay in the superrotating state. And when we do the experiments backward, I mean decreasing Q, then we will follow the upper branch, for which we are on the superrotating state for a very long time. And then finally, it becomes unstable and we go down here back on the normal state. And so here you can clearly see on this axisymmetric model that we have a very nice bistability range. And we understand in terms of orders of magnitude what control the range of this bistability and which are the parameters that might lead to bistability. The other curves are the same by basically changing the friction. So this is just the illustration of the normal states and the superrotating states. And so the point that we have made, I will just go to the conclusion because I am late. But basically, our conclusion here is that we have theoretically characterized the range of parameters for bistability and the abrupt transition to the superrotating state of the atmosphere. So we have verified those results in an axisymmetric primitive equation model. And we are currently working on checking this on a full GCM. Another point I have not discussed today is that the Hadley-Cell feedback, positive feedback, seems not robust and highly dependent on the dissipation parameter, while the Rossby wave feedback that I have described today leads to, might lead, depending on the parameter, to a broad and robust bistability range. And it doesn't depend much on the dissipation mechanism. So thank you for your attention.